So, good evening everyone. So, it brings me immense pleasure to welcome all of you to this SRIBS seminar series. So, this is our flagship seminar program of Srinivasa Ramanujan Institute for Basic Sciences. So, through this series, we aim to bring together the experts and research from biological sciences, chemical sciences, physical sciences, mathematical sciences, as well as computer science. So we encourage thought-provoking discussions and exploring cutting-edge developments in the research areas. So our goal is to encourage rigorous scientific discourse, inspire collaborative research and contribute to the collective knowledge of the community. So myself, Srijit MM, I am a postdoctoral fellow in mathematics in this institute. So for officially inaugurating our program and welcoming our first speaker, I invite our director, Professor Suresh sir, formally. Hello, sir.
You can sit here.
Yes, sir.
Yeah. Distinguished guests, dear faculties, esteemed colleagues, dear students, it is with immense pleasure I welcome you all to this inaugural seminar of SRIBS. As Dr. Srijit already mentioned, so we are starting this seminar series today. Today we are going to have this Kerala School of Mathematics and Astronomy. This is the right?
Yeah.
Okay, so let me. Today, let me introduce Dr. Jolly K. John. He is a fellow of the Inter-University Center for Social Science at MG University, Kottayam. Dr. Jolly is a luminary in the field of history of mathematics, renowned for his insightful research into the Kerala School of Mathematics. His work illuminates the remarkable contributions of medieval Kerala to the world of mathematics, particularly the profound studies of infinite series. Today he will be taking us on a captivating journey through the life and work of Madhava of Sangamagrama, a pioneering mathematician whose genius laid the foundation for the Kerala School's groundbreaking discoveries. Dr. Jolly John's own intellectual journey is equally inspiring. With a PhD in chaos theory in physics from the University of Pune, he brings a unique perspective to his study of history of mathematics. His interdisciplinary approach exemplifies the interconnectedness of knowledge and the boundless potential of human curiosity. As we delve into the world of Madhava and the Kerala School, we are reminded of the enduring power of ideas and the timeless pursuit of knowledge. Dr. Jolly John's presence today guiding us towards a deeper appreciation of our intellectual heritage and inspiring us to continue the quest for understanding. Please join me in extending a warm welcome to Dr. Jolly K. John. So over to you.
When we look at the history of mathematics and astronomy in India, we are all, or most people will know about at least two names, that is of Aryabhata and Bhaskaracharya. But now it is becoming clear that Madhava Sangamagrama of Kerala is an equally important or maybe even a person of greater contribution. And all over the world now people are, historians of science are now looking into the contributions of Madhava Sangamagrama and in particular and that of the Kerala School of Mathematics and Astronomy in general. So what is this Kerala School of Mathematics and Astronomy? Now there is an institute, I think, Kerala School of Mathematics, Government of Kerala. But here we are indicating the presence of a continuous chain of mathematicians and astronomers in Kerala. So by Kerala School we mean this group of mathematicians and their contributions and the science they developed. Now, why suddenly it has become so important to study this Kerala school? That is because people have found out that the most important, or one of the most important branches of mathematics, calculus, actually originated in Kerala. And not only that it was first developed in Kerala, but also that it was developed centuries before similar developments took place in Europe. We all studied earlier that it was Isaac Newton who developed calculus. It is said that during the plague years, Newton retreated from the university to his village home, and there in concentrated thought process, he came up with some of the greatest ideas in science, that is of the law of gravitation and his most famous 3 laws of motion. And also in that time, he laid the foundations of calculus. Now later on there is a big argument or big fight between the supporters of Newton and supporters of Leibniz about the priority, who was actually the first person who developed this branch of mathematics. So the continental mathematicians argued that Leibniz was the first person to develop calculus, whereas British mathematicians argued that it was Isaac Newton who developed. Now the consensus is that both of them independently and almost at the same time arrived at these results. But these things are happening in late 17th century. Newton was born in the same year as Galileo died, that is 1642, and he died in 1727. So that is the time in which the Europeans developed calculus. But we have now evidence pointing that Madhava Sangamagrama in the late 14th century and the early 15th century had actually laid the foundations of this great branch of mathematics called calculus. And we can trace back the elements of the idea of differentiation, etc., to Pascal II's writings in 12th century. So we want to first see what is the context, what is the historical context, and then I will show you how one particular series was developed, how the series for pi, which European historians call as Gregory series. So again, Gregory was contemporary of Newton. Madhava developed it almost 2 centuries or 2.5 centuries before Gregory. So let us see the context of this. Mathematics in Kerala was developed not in isolation, but it was part of the greater Indian development of mathematics. So, who are the prominent early Indian astronomer mathematicians? Again, mathematics was not developed as a standalone science. Mathematics was done in aid of astronomy. So, all these people, all these scientists we are talking about, they are astronomer mathematicians. Their primary concern was probably astronomy, and in aid of astronomy, they developed this mathematics. So, the greatest name in Indian science, early Indian science, is that of Aryabhata, who was born in AD 476. and lived up to probably 550. And Aryabhata wrote his great treatise called Aryabhatiya in AD 499. And so far, this is the most celebrated text in India. So what Aryabhata did was that he studied all the astronomical systems. We know about Panchasiddhantika, etc. There were 5 systems of astronomy here, like Vaidanga Siddhanta or Brahma Siddhanta, Vasishta Siddhanta, Ramaga Siddhanta, Paulisha Siddhanta, etc. So Aryabhata reformed all this and he introduced many new concepts, and his Aryabhatiya was written in 499, and he was probably, it is said that he was only 23-year-old. And who was Aryabhata? He was, we don't know much about Aryabhata. It is, we have to see that it is Aryabhata, it is not Aryabhata. That double T is not there. So we don't know who he was actually, we don't know much background. But it is said that he was from Asmaga country. Asmaga Desha was his birthplace. This Asmaga is where exactly it is not known, but some have argued that Aryabhata was from Kerala. He was probably from the area of Iringalakkuda, that area. That is one argument. Others say he was from Deccan area. Asmaga Desha is actually Deccan. That is another argument. But what is clear is that what is the evidence which he says Kusumapure Abhyarjanam Jnana. So that means he got all this knowledge from Kusumapura. Kusumapura is identified as Pataliputra or near Pataliputra or Patna. And he was a student and later a teacher at the famous university there, that is Nalanda University. So that which is known. Now Aryabhatiya became the celebrated text that was translated into Arabic and other languages. It went to Arabia, and from there the contents were spread in the rest of the world. Next big name is that of Brahmagupta, who wrote Brahmasura Siddhanta in AD 628, and later Kandakhatyaya is also an important work. Brahmagupta's Brahmasura Siddhanta and other work, they were also translated into other languages a century later. And then we have Bhaskara first. Bhaskara first is a person who propagated the Aryabhatan system in India later, after Aryabhata. He wrote the first bhashya or commentary on Aryabhatiya in 629. He also wrote 2 books, Mahabhaskariya and Lekhu Bhaskariya. And then much later comes Bhaskara II, who is more familiar to us as Bhaskaracharya. His Lilavati is very famous. That Lilavati is actually Lilavati, Bijaganida, Grahaganida and Gunadhyaya are 4 works which form the bigger work Siddhanta Shiromani. And then he also wrote Karana Kauduhala. So I wrote, there are many other important mathematicians, astronomers. I wrote these 4 names because they are the most important ones, and these works are later on commented on by Kerala mathematicians. Right? In Kerala, we can say it is, we can almost call it an Aryabhatan school, because Kerala mathematicians give most the highest importance to Aryabhata. And it is his system which they further developed and refined. So we can see there are various commentaries of Aryabhatiya in Kerala. In fact, the majority of commentaries of Aryabhatiya is from Kerala. Rest of India, the number of commentaries are less in Aryabhatiya. So we don't know the reason. So that is again strengthening the argument that probably he was from Kerala. Another thing is that Aryabhata is using Kali version in his notations. but the rest of India, people were using Shaga era and Vikram Samvalsara. So Aribada was using Kali era, which was what people were using in Kerala at that time. So probably he was from Kerala, probably he is not. But the fact is that the Kerala School of Mathematics and Astronomy, the father figure is Aribada. Now, about the Laghu Bhaskariyam, Mahabhaskariyam of Bhaskara first, and Leelavati of course was very famous and very popular in Kerala, and these are also commented on by mathematicians and astronomers in later periods. Now let us see who are the most important figures in Kerala School of Mathematics and Astronomy. We start with Varaduji in 4th century AD. So Varaduji is supposed to be the initiator of astronomical studies in Kerala, or at least what is non-studies. Before that also, people of course had studies. In the 4th century, Varaduji time is 4th century. He 2 points. One, he wrote 248 Chandra Vakyas. These are Vakyas which indicate the position of moon at different points. Where is the moon? How to locate the position of the moon? So he wrote these 248 Chandra Vakyas. And also he is supposed to be the first person who started the Katavayadi system. Katavayadi system is what is used in Kerala to denote numbers in words form. So you can form words. So everything is written in Sanskrit slogans and in Malayalam also. But no number is used. Everything is in Katavayadi system. So you can make poetry, you can make prose of mathematics and astronomy. And if you make it into Sanskrit slogas in compressed form, it is easy for students to memorize it. So this Katavayadi system is supposed to be very old as the 4th century where Varaduji started. Then the next important person here is Haridatta. He initiated what is called the Parahida system of astronomical computations, and it was announced in AD 683 in Tirunamaya. And this is see, by the time of Haridatta, there were some discrepancies which were found in the Aribhadan calculations. So Haridatta improved that Aribhadan system of calculating the position of various planets, etc. And he proposed this Parahida system, which people followed for a very long time. Even now, Jyotish is for Muhurta calculations, etc. In some cases, they use the Parahida system. And his book, Grahachara Nibandhana, is a working manual of the system. This book is available even now, and it is printed. So this 7th century book we have, Grahachara Nibandhana. And then comes Govinda Swami. He was a court astrologer of King Ramavarma Kulashekara, Ravivarma Kulashekara. So he wrote a commentary on Mahabhaskariya. So this is of Bhaskara first, Laghu Bhaskariya and Mahabhaskariya. We are of Bhaskara first. So Govinda Swami's commentary on Mahabhaskariya is famous, and in which he elaborates the ideas of Aribada and Bhaskara. Then we have Shankara Narayana. He was a disciple of Govinda Swami. He was a court astronomer of King Ravivarma, Chera King of Ravivarma, and he wrote a commentary on Laghu Bhaskariya in AD 869. And he mentions that there was an observatory in Mahadapuram. Mahadapuram was the capital of Cheras, Kodungallu. So the observational fact, maybe for the first time we get an evidence, how these results are obtained. So we know that we can develop science only by observing astronomy. We can develop only by observing the stars, observing the planets and other heavenly bodies. So they said that there was an observatory in Mahadapuram. And then we have Uday Divakara in 11th century. He was probably from Kerala. He got a commentary called Sundari on Madhava. Then we have Suryadeva Yajman, either from Kerala or Tamil Nadu. He wrote commentary on Legumanas of Punjava. He was another Indian scientist, astronomer. And he wrote commentary on Aryabhatiya also. And see, he wrote a commentary on Madhava Bhashya of Govinda Swami. So Madhava Bhashya of Govinda Swami is a commentary on Madhava. And Suryadeva Yajvan wrote a commentary on that. So this is how the system develops. You have a basic text Aryabhatiya, you write Orlag Bhaskaryam or Madhavaskaryam, then somebody writes a commentary in which new ideas, commentary, original text is explained and new ideas are also introduced there. And again a commentary on commentary, the ideas are further developed. That is how the system works here. Then we have Govinda Bhattacharya of Kalakkulam. He is famous for astrology. So we have in Kerala the ultimate word of astrology is Payur Kaniyar family. He say anything in doubt, you should go to the Payur Padipura, you can get it answered. So Govinda Bhattacharya trace the origins to Govinda Bhattacharya. Then we have Rudra. Rudra is a guru of more famous Parameshwara of Vadasreni. His works are not identified, but he is quoted by later scientists. Then comes Madhava Sangamagrama, 1340 to 1425, that is his period. He was known as Golavir, master of spheres. And Vedvaroha is a work we have still available, written by Madhava. This is a procedure to read out the true positions of moon every 36 minutes. Now, we can observe the moon, motion of moon. But the moon is not traveling with a constant velocity. So, knowing the positions at certain instants will not give you an idea what are the positions at intermediate positions you cannot get. So, you need elaborate calculations for that. So, Vedvaroha, Madhava gives a method for, we can just read out the positions of moon every 36 minutes using this procedure. Then there are other works which are said to be that of Madhava. Leksha Pragarna is one work, Mahajya Nayana Pragara and Madhyama Nayana Pragara other works. Aganida is probably an important work in which nowadays you can make calendars of 1,000 years. So this Aganida in that book, Madhava was giving method of making calendars for centuries ahead. But the book is not available now. Now we have Parameshwara Vadasreni. He is an important figure. He revised the Paraheda system and introduced Dirganida in AD 1430. So Paraheda system, by his time, 15th century, there was a lot of discrepancy between what the theory said and what direct observation was showing about the positions of planets, etc. So, Parameshwara was a great observer of astronomical objects. He observed for 55 years on the banks of River Nila and also on the seashore. Because of that, he got there is a story that he got excommunicated from his community because he was interacting with the coastal people for his observations. And he wrote about 30 books. And he was also an expert in eclipse calculations. He observed a large number of eclipses and its details are given in Siddhanta Dikika. Then we have Chandrachaya Ganida on the computation of moon's shadow, the shadow of moon on Earth. And he wrote commentaries on Aribhadiya. His commentary on Aribhadiya is very famous. Even in rest of India, it is a very famous book. And on Mahabhaskari and Surya Siddhanta also, he wrote commentaries. And then we have Damodara Padasani, who was Parameshwara's son. And his student, Nilakanta Swamiyaj, is the most celebrated astronomer probably in Kerala, in the Kerala school. Because of his great works, Tantra Sangrama, which was written in AD 1500, and his Aribhadiya Bhashya, which is probably even a greater work. Tantra Sangrama was written in 1500 AD. Yes. This is the time at which Europeans are coming. 1498, Vasco da Gama landed in Kozhikode. So at that time, the greatest book on astronomy of the times was written by Nilakanta Swamiyaj. And he has other books, Siddhanta Darpana Vyakhya, Grahana Nirnaya, Chandrachaya Ganida, Graha Parikshakrama, Golasara. These are the important works, out of which Chandra Sangra and Aribhadiya Bhashya are the most important ones. Now, Nilakanta, this Chandra Sangra is a book on astronomy, and in which he uses the most advanced mathematics of the time. And where did he get this mathematics? He does not claim that he developed all this mathematics. Very important verse, he says, it is from Madhava. So it is coming down from Madhava Sangamagrama. Now we have Chitrabhanu, he wrote Karanamurda, Advanced Manual on Astronomical Computation. Then Narayana, pupil of Chitrabhanu, his Uparaga Kriyakrama is famous. Then he also co-author of Kriyakrama, that is another important work. It was started by the next astronomer, mathematician Shankaravairya, and Shankaravairya could not complete it, Narayana completed it. And Shankaravairya was a student of Nilakanta. His Lagu Vibhrati is an important work. Then we have Jeshtadeva. It is because of Jeshtadeva that we know about these works now, because Jeshtadeva wrote the famous book Yukti Bhasha. And the importance is that Yukti Bhasha explains the rationale behind the mathematical results. Madhava gave the results in condensed form in slogas. Nilakanta used them in Tantra Sangraha for calculations. But what is the rationale, what is the yukti of these results? Or how did they get those results? That is explained in Yukti Bhasha. And it is written in Malayalam language. Till then, all the texts were written in Sanskrit. Even after this was text, majority of them were written in Sanskrit. But Yukti Bhasha is written in Malayalam, and this Malayalam is very close to the modern Malayalam which we use. So, the studies of Yukti Bhasha will change the concept of or idea of the language itself, because we mostly think that till recently it was more influenced by Tamil or other, even the scripts were influenced. But you can see very good Malayalam, very close to the language which we use. And he is explaining the rationale, yukti of the results, mathematical results. But these are in prose form, there are no equations, there is no diagram. It's in prose form written. So you need somebody else again to explain that, right? So Tantra Sangraha uses the most advanced mathematics of that time. Yashadeva explains that in pure Malayalam. But today we can understand it because of a further commentary or Iktibasha written with a lot of footnotes, that is by A.R. Akhileshwaraya and Ramavarma Maruthamburan. They published it in 1950s. Mangaladevam was published. That is the text which is now we are using. So in this Ramavarma Maruthamburan and A.R. Akhileshwaraya, they have systematically explained the mathematics, how various formula are derived. I will be following that text. Then we have Shankara of Vishnungaram, mostly he wrote on astronomy and astrology in Malayalam. So by this time, works are now increasingly written in Malayalam. And then we have famous Achyuta Krishnaredi. Achyuta Krishnaredi is famous because for the first time, reduction to the ecliptic, for which Tycho Brahe is famous. So that was done almost at the same time in Kerala. That is, all the planets are not exactly moving on the ecliptic. So you have to reduce their position to the ecliptic for the studies and comparisons. So that was done by Achyuta Krishnaredi. You got various books, Puranamaya, Rashikoda's Puranidhi, and there is a commentary on Sudi Siddhanta. Then we have Idakamancheri Nambudiri, author of Bhadradiva Ganitha and Bhugola Nyaya. And in this, there is a mention of armillary sphere, etc. Armillary sphere is a device used for astronomical observations. Then we have Purushottama, in whose work we can see computation of solar and lunar eclipses. He used his own device multipliers, devices, and other constants. Then we have, coming to more recent times, Kochikashnasan, who wrote a commentary on Aryabhadiya in Malayalam. For the first time, a commentary on Aryabhadiya is in Malayalam, and it could also Malayalam work Kanakku Shastram. Then Khadigopa, he also writes a commentary on Aryabhadiyam in Malayalam, also in Sanskrit. Then Shankaravarma of Kadathanadu, he was a prince of Kadathanadu royal family. He writes the famous book Sadratna Mala in 1823. This is a compendium of results of Kerala astronomy and mathematics. You can see it's a summarized version of all the results till that time. And then we have A.R. Rajarajavarma, who is famous for his literary work, but he also wrote Karana Parishkarana and Panchanga Shuddhi Badhari, Jyotisha Pragashana. So he was introducing whatever corrections were necessary, probably based on modern ideas. And Purnashiri Nilakanta Shastri is there. Purushottam Nambudiri of Chennannur, P.S. Purushottam Nambudiri. He synthesized the modern Western system and the traditional Indian system and wrote books. And as in 20th century also the tradition continues. K.V. Ramapuduval, he wrote Ganitha Pragashiga, and Punyakanda Puduval writes Shuddhadari Ganitham in 1956. So we have from 4th century Vararuji to 20th century an uninterrupted chain of mathematicians and astronomers. Right? Now, many of these people were doing probably for astrology, we don't know, but the results are not used only in astronomy. We have we have evidences of this used in navigation, and if you have a good calendar that helps in agriculture. So in various fields of life, the results were used. What are the most important results in modern times when we look back, we see some of this, all these results are not unearthed now, we don't know what is there. There are, K.V. Sharma has identified, he has published a catalogue of about 700 texts in Sanskrit and Malayalam on astronomy, astrology and mathematics. And many more are there, whatever he could collect, going into various illums and other places. He collected these books, and hundreds of them, or many, more than that, they were destroyed because he writes in one of his articles, somebody says there is a huge collection of manuscripts in one volume in Thrissur. He reaches there, he opens the boxes, but everything is eaten by white ants. So like that, hundreds of books are gone, but we have many books, hundreds, 700, 800 textbooks now, out of which people have studied maybe less than 1 dozen. Now, what are the results we can see? One is interpolation rules. Govinda Swami in 9th century, he gives the interpolation of functions, like if you know f of x, how to find f of x percentage. This is the same as Newton-Gauss interpolation formula. Then Taylor series expansions. Brooke Taylor gave this expression for Taylor series. Madhava Sangamagrama gives this for function f of x if it is sin x and cos x, then what should be the expression? Then we have the tan inverse x formula, tan inverse x series. This is a series, not terminative, it is a series.
See, there in the previous one, they also use the term sin x, cos x.
No, they use different terms. Sin is jiva, jiva and sin, right? It is said that jiva, when it went to Arabic, it became ziva. When it went to Latin, it became zina. When it went to English, it became sin. So jiva is the original term, right?
So for all these, there are corresponding.
Now, all these are in Sanskrit verses. We have to
Okay. Interpret.
decipher it. Right?
It's like another commentary.
So by studying the commentaries, we can get what is written there. Right? And all these numbers, etc., will be in Rabajali system notation. So we have Leibniz power series for pi by 4 or degree series. Then the idea that pi is irrational was given by Nilganda in Aribadiya Bhashya. He says we cannot find exact values, only approximate values. Asanna values can be found out. Right? And then a number of series, different series for pi, we can find in these books. So Madhava first gave the infinite series expression for pi, and these different series are there in Yukti-Bhasha, Madhava Sangamagrama, etc. Many of these series are not found in Western mathematics, and they used very clever methods to find the series and exact values of pi. Then Nilganda was a pioneer in the study of infinite geometric progression. I will show you that. Then Parameshwara in 15th century gave expression for the circumradius of a cyclic quadrilateral in terms of its sides. Then, as I said, Achila Prasharides reduction to the ecliptic, which is in West known as Tycho Brahe's contribution. Then sine table. So every student is using logarithmic tables in which sine table, sine, cosine, etc. are there. Aribada gave the first sine table in India, in Aribada, and Kerala mathematicians improved it, improved the accuracy, more and more accurate Sign tables are given. Madhava gave the most accurate one. 11-digit accuracy of pi is implied. For finding the sign values, you need the value of pi. Right? So if your pi is more accurate, your sign values are more accurate. Then in Madhava Bhasha, Nilaganda developed a computational system in which the inferior planets are revolving around the sun, and then all of them together are revolving around the earth. So this is the precursor to the heliocentric model of the solar system. And then binomial series expression, Bhasha was a way of finding out what is 1 plus x to the power minus 1. Right? So here, this binomial, Newton is famous for binomial expression. For positive integers, binomial theorem was not much before Newton, but Newton generalized it to negative and fractional powers. And there is a story that in Newton's tomb it is engraved, the binomial expression is engraved. Probably it is not correct, but it is a story which is showing the importance of binomial theorem and importance which Newton gave to it. Then estimation of sums of powers of integers. So that is again, I will show that 1 plus 2 plus 3 plus first up to n. What is the power? What is the sum of squares of integers? 1 square plus 2 square plus 3 square. What is the sum of cubes of integers? And then we can generalize it, precursors to, that is how these people were led to the process of integration. Then of course there is instantaneous velocity of planets, etc. Now let us see the actual mathematics, development of infinite series. So Nilaganda tells us how to generate an infinite geometric progression. Right? So here, take this number 3 by 7. This number 3 by 7 I can write as 1 minus 4 by 7. Right? This 4 by 7 I am writing as 4 by 3 into 3 by 7. My original number is 3 by 7. So I have written it as 4 by 3 into 3 by 7. And for 3 by 7 I can write this 1 minus 4 by 7. So 4 by 7 is expanded in terms of 4 by 7. Now this 4 by 7 I can again substitute this. I can go on doing this. Right? So an iterative method is found out. For this 4 by 7, I substitute this expression. And the next 4 by 7, again I substitute this expression. Like that, I get the geometric progression, infinite geometric progression. So for convergent GP, this method is given. Right? And this is the crucial method, very simple one. Anybody can do it now. School students can do it. But this was a sort of starting point. Now let us generalize this. I write it as C by D. Numerator C is less than B. B is a bigger number here. C by D I can write as 1 minus B minus C by D. 3 by 7 I wrote as 1 minus 4 by 7. Now this B minus B upon B, I multiply and divide by C. Again I get C by D here. For C by B, I can put 1 minus B by B. So B minus C upon B, again I get in terms of B minus C upon B. So I keep on substituting, generate more and more terms. I get this series for C by B. 1 minus B minus C by C plus B minus C by C square minus B minus C by C cube, and so on. Higher and higher powers. Now I put B minus C by X, or B minus C upon C as X. I have the series. Suppose I put this as X. So this is 1 minus X plus X square minus X cube. Left hand side is C minus B. What is that C minus B? I am putting B minus C by C equal to X. So B by C is 1 plus X. So C by B is 1 by 1 plus X. So my LHS is 1 by 1 plus X. So I have the expression for 1 plus X to the power minus 1. 1 minus X plus X square minus X cube, etc. Right? So this is what was developed. Obviously not in this terminology, but the idea is same. This was developed probably at the time of Madhava, or the 11th, 14th century, 15th century. Now, it is probable that Newton started from this binomial in arriving at his general binomial theorem. Because
independently. Independently. Or
could be independently.
because he may not have access to this.
We don't know, because people are always traveling, isn't it? People are always traveling.
But it was in another language.
It was in another language, but we have intermediaries. For example, the Syrian Christians were always in between the West and East traveling. So in 7th century, there is a Syrian bishop who is telling people there, the European people, that you don't have any mathematics, you don't know any mathematics, look at the Indians. This is in 7th century. He was a bishop of the Syrian church, because people were coming here. That is one way. Plus Arabs were coming. Arabs were coming. Even a couple of months ago, a number of Roman coins were discovered somewhere in central Kerala. Roman coins. Roman coins. So, before Christ, in the first centuries, the centuries of BC, the Roman settlements were there in Kerala. So, these ideas will travel to and fro. Ideas can come from there, ideas can go from here. So we don't know what happened. So far there is no evidence that Newton had any kind of knowledge about these things. But indirect way of transmissions are possible. Right? Jesuits were active in Kerala. 1498 they were here. And Newton is coming almost 1.5 to 2 centuries after that. And Jesuits are known for their love of knowledge, collecting of manuscripts, etc. So there are people inquiring about that route of transmission of knowledge. So far there is no evidence. Right now we should assume that this was an independent development in Kerala and there was an independent development in Europe until there is evidence. Now, let us come to the next step, the most important step Kerala mathematicians took. Here, this is 1/4 of a circle. If you can find the length of this, you can find the circumference. Right. Now, how to find the length of this circular arc, or 1/4 of the circle, or even half of this. This is a diagonal here. So basically, the 1/8 of the circumference, this length, that is what is to be found out. Now this is the ancient problem, squaring the circle. And squaring the circle means you are trying to find the area of the circle. So that is what the kids, etc. were trying mostly. But here, Malayali side, so Kerala school people were not finding the area, they were trying to find the circumference of the circle. In both these, value of pi is needed, or value of pi is implied. So
at that time the pi value was also known. Pi was known as
pi, Arivoda is giving pi value 3.1415.
How did they arrive at pi? That is.
What is pi? Pi is the ratio of the circumference and diameter.
In that sense,
Right? That is pi. So, given a diameter, what is the circumference of the circle? This is the question. And nobody can exactly find that. Or you cannot exactly find the area. So here, given the radius r, this is the circle. This is the center of the circle. So radius of the circle. Suppose you know the radius. What is the circumference of the circle? That is the question. So this is 1/4 of the circle, half of that is this, 1/8. Now what is done is, this is a square. So this is the radius of the circle, means this PQ is also radius, equal to the radius. This PQ line segment is divided into large number of small segments. Each say delta x. Each length is delta x. Now we draw, they say Karnas diagrams to these points P1, P2, etc. After each delta x, we draw a line. Another delta x, draw a line to the center. Like that. So idea is to divide this PQ line segment into a large number of very small segments. So Yukti Bhasha says, assume that this number of segments is Parartham means 10⁻⁸. Right? So they are going to the concept of infinity. And when you divide this into large number of, the number reaching infinity, large number of segments, each one is infinitesimally small. So that is the whole idea of calculus. You are dealing with infinities and infinitesimally small quantities, and also the limiting process. Right? So all that is coming here. All that is coming here. So these lines are drawn, and to this Karnas, K1, K2, K3, etc. perpendiculars are drawn from this point. You draw a perpendicular here, and from here draw a perpendicular, from here draw a perpendicular, like that. And in terms of this radius and this K1, K2, etc., we can find what is this length P1 or P1. This is make it bigger. So idea of
P1, P2, P3.
similarity of triangles will be used here. So
Those are P1, P2,
P1, P2, P3 is P1, P2, P3.
P1, P2.
P2, P3, etc. This is Q1, Q2, Q3, etc. Now, if you look at this triangle OPP1 and this triangle PQ1, P1, this small triangle and this triangle, they are similar triangles. And from that, we can find an expression for this PQ1 in terms of this side R and this K1. Right? So like that, we find expressions for PQ1, P1, Q2, P2, Q3, etc. So, from considering the similar triangles, that PQ1 is R delta X by K1. P1 Q2 is R delta X by K2. P2 Q3 is R delta X by K3. So R is this equal to radius of the circle. These are K1, K2, K3, etc. So these segments are now written in terms of R, K1, K2, K3, etc. Now, from this point here on the circle, we will draw a perpendicular to this curve. From this point, a perpendicular will be drawn. Like that, number of perpendiculars will be drawn. Here, one is missing. So already this is there, and this is another line segment, another line segment. The idea is that if you add this line segment, this, here one more, this, and so on, all of them, you will get the circumference. Now this line segment we will express in terms of this lines, which we already know. We have found out these upper ones in terms of R, K1, K2, etc. Now again we will use similarity of triangles. For example, O, P1, Q1 and O, A1, B1 are similar triangles because this is a perpendicular here, this is also perpendicular here. So this triangle O, P1, Q1 and O, A1, B1, they are similar triangles. So we can now express this line segment A1, B1 in terms of P1. So that is what is done next using this similarity of triangles. So that A1, B1 will be P1, Q1 into R by K1. P1, Q1 we already found out, that is R delta X by this is the next K2, second one we have taken. So this we retain as such, and next one is in terms of this. So K2 is like. So we have expressions for these. A1, B1 is R square delta X by K1, K2. Next is R square delta X by K2, K3. Next is R square delta X by K3, K4 and so on. Now we sum up all these line segments. We will add first one, simply R delta X by K1. Next is R square delta X by K1, K2. Next will be R square delta X by K2, K3. Next is R square delta X by K3, K4 and so on. We will add from here to here. Then we will get circumference by 8. Circumference by 8. And in the limiting process, in the limiting case, this will be exactly equal to the value of circumference by 8. But there are other techniques here. So circumference by 8 is sum of all these line segments, R square delta X by R K1, R square delta X by K1, K2 and so on. Now these products K1, K2, K2, K3, K4 etc. you have to remove. So we can remove those products because K1 is this diagonal, K2 is this diagonal. Delta X, in the limit delta X approaches 0, there is not much difference between K1 and K2. Right? So if you assume delta X to be very, very small, then K1, K2 minus K1 is almost equal to 0. I am expanding this, K2 square plus K1 square minus 2K1, K2 product. This is the product. 2K1, K2 equal to 0. So K1, K2 is K1 square plus K2 square by 2. 1 upon K1, K2 is 2 by K1 square plus K2 square. Again a little manipulation. I multiply and divide by K1 square plus K2 square, and denominator becomes K1 square plus K2 square square. That should be square of 2k1 k2, that is 4k1 square k2 square, dividing, I get this as half into 1 by k1 square plus 1 by k2 square. So simple manipulation gives me 1 by k1 k2 is half of 1 by k1 square plus 1 by k2 square. This we will use in the previous one. We have this k1 k2 k2 k3 times etc. So you will write them as sum of two terms. Each one will be written as sum of two terms. This also here instead of 1k we will use r, that's all. So that is done. So our circumference by 8 is, first term becomes half r square delta x by k1 square plus r square delta x by r square. Next is in terms of k1 k2 and so on. Last karna is the diagonal OQ. Now this term and the last term are different. Other terms are repeating. So there is a series here. There is another series here. Difference is only in these two terms. And the difference between this whole and this whole is the difference between these two terms. That difference is very, very small because OQ is a diagonal root 2r. So this is 2r square. This is delta x by 2. Here this is delta x. So difference is delta x by 2. Between this series and this series, difference is very, very small. So we neglect that difference. So we can write it as just the double of this second half. Just the double of the second half. And that is written. So you have c by 8 as a series here. Now each of these terms will be converted into an infinite series. How do we convert that into an infinite series? We know that if you look at this triangle, this is R, this is K1, this is delta x, this is a right angle triangle. So K1 square minus delta x square will be equal to R square. Right? In the next, if you look at this triangle, K2 square minus 2 delta x square will be equal to R square. So we use that property. Now, this term is r square delta x by k1 square. If I take delta x minus delta x into delta x square by k1 square, delta x is common. This becomes k1 square minus delta x square by r k1 square. K1 square minus delta x square is r square. So this is delta x r square by k1 square. Or delta x r square by k1 square, the first term, I can write as delta x minus delta x into delta x square by k1 square. This will be used iteratively to generate a series. Right? Because r square delta x by k1 square. Here also delta x square, delta x is coming, k1 square is coming. So for this we can substitute again. So r square delta x by k1 square is delta x minus delta x by delta x into, I multiply and divide by r square. So I again get r square delta x by k1 square. Here I will substitute the same expression. So we generate a series here. For the first term here I get the series delta x minus delta x square by r square, delta x cube by r square, this is delta x 5 by r to the power 4 like that we get a series, and for each term a series will be there. In the next term it will be 2 delta x square which is coming, because that was from a bigger triangle. 2 delta x square will be coming. Now when I substitute for all these terms, each is replaced by an infinite series. So for this first term I have a series here, infinite series in delta x terms. Second term I have a series in 2 delta x terms. Third term I have a series in 3 delta x terms, and so on. By adding all this series, we will get the circumference by h. Now look at this. Delta x is the first term in all this series. So I add delta x, delta x. Second terms I write here in that delta x square here, 2 delta x square here, 3 delta x square here, and so on. In third terms, I have delta x to the power 4 here, 2 delta x to the power 4, 3 delta x to the power 4, and so on, like that. Now, all delta x's added together will be equal to radius r. Now that line segment was equal to r. So the first sum of all delta x will be equal to r. Now, here we have delta x square, 2 delta x square, 3 delta x square, etc. Now what Yukti Bhasha is saying that, imagine there are extremely large number of segments. Parartham is the word used. So of the order of 10 to the power 18, or they are meaning infinitely large number. And assume that delta x is unity. Right? In that case, if delta x is unity, this becomes 1 by r square into 1 square plus 2 square plus 3 square, etc. This becomes 1 to the power 4, 2 to the power 4, 3 to the power 4, etc. This becomes next power, even power 6, and so on. Now, these sums, they have formula for these sums. So I don't think we can go to that. So this is what they call Sangalita. 1 plus 2 plus 3 plus 4 plus etc. That is Mula Sangalita. So there they have derived a formula from that. Varga Sangalita is 1 square plus 2 square plus 3 square plus etc. Formula is derived from that. I will show the formula. So Mula Sangalita, sum of all these natural numbers, that is turning out to be n into n plus 1 by 2, you know, if n is a finite number. If n is a very large number, infinitely large number, then n plus 1 is almost equal to n, so it becomes n square by 2. And the next case they use this formula. So Varga Sangalita is sum of squares of these numbers, and using the formula for S1, they get the formula for S2 again. That is very interesting calculation here. So this squares, sum of squares of natural numbers, that will be n cube by 3. And sum of cubes, they found out, that is n to the power 4 by 4. And remember, this n is actually, what we did is dividing this into small segments. We are finding delta x, 1 delta x, 2 delta x, 3 delta x, their sum, and 1 delta x square, 2 delta x square, their sum. So this is in a way equivalent to definite integration. A definite integral. Integral x dx is x square by 2. 0 to n, if you put n square by 2. This is 0 to n will give you n cube by 3 and so on, these same expressions. So they have arrived at a way of obtaining this integral formula, right? And this is used in the calculation of circumference. So in this, first one will be r cube by 3, right? So we are dividing that radius into large number of segments. So this will become r cube by 3, this will become r to the power 5 by 5, r to the power 7 by 7, and so on.
This in that formula, previous. These are all plus signs because
These are all plus signs.
then it becomes a huge number. No?
No, this is not plus. This is minus, this is plus, next will be minus. Alternate signs. Alternate signs. Inside it is plus.
Inside everything is plus.
Plus. Outside it
Then
is
inside it becomes a kind of infinity, no? Infinity by r square.
No.
Because one
That
square
is
plus
because
two
your
plus three square.
as the number of segments is increasing, your size of delta x is decreasing, isn't it? So n delta x is equal to r. So you increase n, delta x will decrease.
So 1, 2, 3 here is not just numbers.
No.
So okay, so you change delta x as 1.
Yes. Delta x is taken as 1. That's why we are getting this. So but the delta x is there. So we put this Sangamagrama formula here. Once you put that, we get circumference by 8 is r minus r by 3 plus r by 5 minus r by 7 and so on. Circumference is 2 pi r. If you take it in modern notation, 2 pi r. Then what do we get? R will cancel. Pi by 4 will be equal to 1 minus 1 by 2. Formula is missing expression. Okay. So pi by 4 is 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on. That is the formula. That is the expression. So this is the infinite series which they got. And using this, one can calculate, they were trying to calculate circumference. Now we can equivalently calculate the value of pi. But this is a slowly converging series. It will take years to calculate pi to any accuracy. So certain ingenious methods, clever methods are used by Madhava. We call it samskara, corrections terms are introduced and make it fast converge. And with that technique, they calculated pi. Probably Madhava calculated to 8 digits, I think. Later on in Sadhirathamala, 17-digit accuracy is given. And I have shown in there was a conference in Madras, 500 years of Tantra Sangrama. So there I have shown how Vikrasha is using all those samskara to get a value of pi up to 17-digit accuracy. How Shankar Varma got that 17-digit accuracy. So that is by introducing this correction types to the series. So series, infinite series is obtained here for pi. And that is there are other series, power series for sine, cos, etc. And sine expressions, etc. Number of series are there. And it is through this series, power series, expressions of trigonometric functions, etc., that Newton developed calculus. So there is close similarity here between the way the Kerala mathematicians and astronomers developed calculus, and Newton developed. Leibniz did a slightly different method, I suppose. So we have to study this in more detail. For example, how there is a little bit of confusion there in the way can you interpret it as an integral or not. Earlier when I started this work after my PhD as a postdoctoral, people were not calling it as integral. Now they are saying this is integration. Now the scholars have come to the conclusion that this is actually integration, which they have done. One can look at it in detail. The point is that there are a lot of things have to be studied here. What is the wealth of knowledge which we had here? We only know some bright spots only. There may be other bright spots lying undetected, and a lot of details are yet to be studied. And more people need to study this. Government should fund it, and institutional mechanism should be there. Our own history, intellectual history of Kerala, to a great extent, will be rewritten when this is completely understood. Thank you.
Thank you, sir, for the very informative session. So now I invite for the question answer session. If you have questions or you have some discussion to be made.
Yeah, ask for online any class.
Yeah, so
Thank you for your very informative seminar talk regarding the history of Kerala mathematics. With this knowledge, what do you think about the future of Kerala mathematics? This is one question from a candidate known as DJM.
Can they hear?
yes.
The future of mathematics will depend on what is the state of current mathematics.
Yeah,
Right?
exactly.
This is an inquiry into the past. So, the idea is that, see, if we know that our own people had developed all these things, the students will get further motivated to do mathematics or science here. Science is not something which is external to our land. It is not something which the Europeans brought to Kerala or something like that. It went from here to Arabia to Europe and came back after a circular travel, probably. So it will motivate people to study mathematics more in Kerala and make much bigger contributions than what we are making now.
There may be more things to explore from
There
the
are
old ones.
lot of
There
things
also you mentioned.
A lot of things are to be explored.
Explore from the old mathematics also. Okay. So these all developed through what is that? Their curiosity to understand the astronomical objects, or most
Astronomy,
of the time.
astrology is also very important.
Astrology.
Astrology played a
Astronomy is also science,
Mhm.
like astrology.
Astrology we don't treat as a science, but to do
How is it
astrology
related to
is like
astrology?
in this system, you need to know that the
Positions,
time,
time.
exact time and position, isn't it? What is Janma Neram?
No,
And that time, what are the positions of where is Shani, where is Budhan, and all those
Okay,
things.
so it is related to astronomy.
Yes. So
Calendar.
first you should calculate, find out what is the position of these planets. For that you need astronomy.
So mathematics is very intricately related to this astronomy.
Yes, yes.
What is the historical reason for that? Like, why astronomy is that true in Kerala? So that was dominating so much.
Astronomy was there everywhere. It is not in Kerala, but people here developed these ideas or pushed these ideas to a very high level. Their purpose was to improve the accuracy, right?
Of the astrology.
So,
Sorry?
maybe they wanted to have better predictions, astrological predictions.
But
Now we say it is
But
not
is-
scientific.
Is there any relationship between these planets and
That
Saturn?
that is
That is
that,
astrology, right?
that is astrology. Now we don't see any.
Anyway,
another thing is
that was a belief.
That was their belief.
Yeah.
other than the astronomical connections.
But more practical reasons are there. Like you want to go out in the sea.
Yeah.
You want to know what is
Yeah.
your position in the sea. You have to depend on stars. So for that practical reason also astronomy accurate calculations are necessary. Or you want to improve the calendar. Means,
In the case of Newton, is there any connection like that?
Newton had no connection with astronomy.
This kind of.
Connection is here with gravitation.
Yeah. So, in all these their mathematics, probably there are some discrepancies or some mistakes also could be there, or
Mistakes will be corrected.
Corrected
By observation.
observations.
This is why
Further compilations.
one person observing the skies for 55 years, he comes up with a new system, Vrigarga. And this Parameshwara was observing for 55 years. So they were doing observations using armillary spheres, etc., instruments. So all these have to be reconstructed. Like armillary sphere construction given in one text, in the museum we can reconstruct it and keep it.
Sir,
Right.
Madhava and Aryabhata, were they contemporaries or
No.
only the
Aryabhata was in 5th century. 499 he wrote
Okay, after
this.
that came Madhava.
Almost 800 years after Madhava.
Madhava lived.
After Aryabhata, 800.
After 800
After 800 years.
Aryabhata was the first Indian
Oh.
scientist
Who contributed?
who contributed.
Okay.
So like Aryabhata gave sign table, very
Yeah.
crude one.
You were saying
So
Madhava is
Madhava improved it to a great extent.
Initially I thought Madhava lived.
No.
They can.
We haven't heard the name Madhava.
Now, in the last 20-25 years, only people started hearing all this.
So is there any other symbol we used for pi? Is there any Indian pi kind of symbol? So this.
Pi-
Did we used any symbol for pi?
Symbol, I don't think so. For pi, there was no symbol. I think. These pi values are implied in this calculations. So what they are saying that if you consider a circle of radius such and such value, then this will be the circumference.
Okay.
From that we calculate the value of pi and say that this is the implied value of pi.
So in the Vedic text, they always say the circumference,
Circumference.
divided by
There is
perimeter divided by circumference kind of things.
no, they will give the radius or diameter, give the perimeter. Then we can see what is the value of pi there. So the value of pi or up to how many digits accuracy pi is known to a people, that is a measure of their scientific advancement. We can say that. How much advanced they are. So like Archimedes gives a method of finding the circumference. How? Because he will take inscribed polygons and circumscribed polygons. Then you measure the length of these sides of polygons. Then double the number of sides. Again calculate the total length. Again double the number of sides. And that
Infinite sides.
that limiting case you will get the correct value, that is it. So that is how in the Western world they found the value of pi. Right? So when somebody spent decades in calculating pi to 6-7 digits, here we have 17 digits accuracy. And the 17-digit accuracy we can improve further because it is an iterative process. So that is what this iterative methods, these Kerala mathematicians were very good. They mastered that. So pi value we could have improved to any level, but more than 17 digits you don't need to calculate sine or cos or even for any other practical purpose. At that time it was not necessary, so they stopped at that way.
The Kerala mathematicians are not generous to distribute their knowledge as compared to Europeans. So,
No, depends on the social system.
Not only that, I mean,
Depends
if you
on the
look at
social-
these scientists, they are all from a particular community. I mean, those who know know about
No, this
Sanskrit,
is
they
initially it was in the Brahminical elite section.
yeah, elite section only.
But then once they started writing in Malayalam,
Yeah.
it started spreading.
What
Right.
Arjun said is also correct because they were not ready to share this knowledge or spread the knowledge to.
No, there is Shankaravaya,
David.
there is
David.
there is
David.
Achyuta Prasharidi.
To
So
spread David.
and later on the Ganaga, Krishnanashan, etc. they were
To
With the
understand.
higher.
Ganagas.
Yeah.
So it's gradually spreading. Right, modern times it is spreading. But it is true that it is in India in general knowledge was confined to certain people.
So
Yeah.
if you see for a historical question, like if you consider like this way, like if you omit this elite section, who is the most famous from the non-elite and so forth? Mathematicians
Means Aryabhata, I want to inquire about that little further. Aryabhata, who say like in Pune, Ayuka, there is a statue. They have taken Aryabhata to be Aryabhata, right? So nowhere it is said that Aryabhata.
Now you
So,
can actually
and at that time, Aryabhata studied in Nalanda. Nalanda was a Buddhist university. Nalanda was a Buddhist university, and but they admitted everything. So whether Aryabhata was Buddhist or Hindu, we don't know.
at least we need to know Sanskrit to understand these things.
Sanskrit,
Sanskrit was known to only some elite group of people. And all the mathematicians
lot of-
that way that we have shown these names are all from that elite group. So who actually, so from the non-elite group, who is the best non-mathematicians?
For that you have to come to modern times.
Somewhere
There is also, you said about Aryabhata and Aryabhata, confusion is there. Probably with the historical, if you trace the history with the, some knowledge in that, I don't know, you have to collect all those data and then it is possible to do some machine learning approach or artificial intelligence approach. Through that, probably you can prove which is correct, Aryabhata or Aryabhata or some.
No, that is more. Now we are concerned about what is the mathematics they developed. What is the
Even that
the
also
first,
is possible. Similarity
this kind of studies will be more of social science
Yeah,
perspective, historical, sociological, and those things. So right now, I'm looking at the mathematics part, right?
Yeah.
So I also want to.
The interpretation that you are doing these equations, it is your own.
No, this is all coming from the edition of Yuktibhasha. These interpretations are given by these two people, A.R. Akhileshwaraya and Ramavarma Merutambre. And whatever is missing part, I have.
So, but you
That's-
mentioned one as
huh?
Yuktibhasha, just not with the numbers, no? One person created the first Yuktibhasha. It was not like
That
this.
is written in prose.
In course.
They will say Trigonam Kakhaga. We say triangle ABC, they say trigonum, kakhaga, or chaturasram kakhaga, like that.
Sir, is there any mathematics journal where people actually publishes this work, or any history journal?
Indian Journal of History of Science is there.
Okay. So how will they review it actually? For example, will we send the Tadiolas to them or photos of them? So there should be a checking anyway. So if I read a Tadiola and I interpret he said integral x square plus 3x equal to this. So how will the other way they review this?
How about this?
There are people working on this. There are people who studied this.
Okay, so people usually send the Tadiolas also to the
No. You take only the relevant parts.
One more place you
You can take
focus.
copies.
One more place you can focus is like you mentioned about the iterative process. No? Actually, Kerala School of Mathematics, there is a strong contribution in the iterative process, mathematical iterative process. So numerical methods.
These can be used
The integration that is
generalized.
iteratives. So contributions to that also, only one section is there.
Do we have access to all these Taviolas and all these? Are they in the
There is a
Wikipedia somewhere?
manuscript library, Trivandrum Kala University
Okay.
manuscript library.
Because he asked about referee.
So,
that's why he asked.
and I don't know now
Maybe we
whether
can
it is
get the copy
digitized.
online or something.
Digital copies, some books may be available. I used to go to
But we should know
the
the
library
language.
and take the. And there is Tripunithura Sanskrit College library is there.
What is chai?
Chai only.
Namadana conclude. Will conclude it now. Will you give a lot of thanks? That's it. You proceed. Yes.
So we come toward the concluding section of our first seminar. So I invite our director to present a memento to our first speaker. Sir, please come.
It was very exciting.
We enjoyed.
Professor Rachel ma'am to give word of thanks.
Good evening, one and all. Respected Director of SRIBS Seminar-Webinar Institute for Basic Sciences, Dr. Suresh C.H. Most distinguished guest speaker of the day, Dr. Jolie K. John. Participants online and offline. Actually, as Srijit mentioned, this is our first seminar in the SRIBS Seminar series. And actually, I am really privileged to be part of SRIBS and also privileged to be proposing the vote of thanks at the first seminar at SRIBS. Sir, this has been really enlightening because it's for the first time I am listening to a seminar of this sort where all the historical developments of mathematics, mathematical calculations, its intricate, this attachment to the the basics are attached, or mathematical developments are depending on the astronomy. All these things I am listening for the first time, and I am sure that because you are saying about the contributions by scientists or researchers or genius people from Kerala, this has been, as you yourself said, this has been a motivation to our young scientists here to contribute more to basic science. And also, I think the various infinite series and all these, actually we have studied it as part of mathematics, but not as something that evolved from all these, like something like this Taliola, or from all the you said from prose and like that, or was it from was it rhythmic and all that in the first? Slogas and all that. So it has been really interesting to know about all these things, and I hope that more things will, or more developments will come out of all these, and we will come to know more about what we Malayalis or Indians have contributed to this field. So thank you very much, sir, for investing your time with us. I really say investing because I hope that this has been a motivation to all our students. So thank you very much for that. And formally, I propose our heartfelt gratitude to you for coming over and making this presentation. And as we all know, our director Suresh sir is behind all this, encouraging all of us, inspiring us, and we have all seen the great change that is coming to SRIBS and that has come to SRIBS after his appointment as the director here. So we hope that as he envisages, he will be able to take SRIBS to be one of the top tier institutions in Kerala. So having him as a visionary director here, we are really privileged to have him. So sir, thank you very much for all that you are doing here for all of us, all the students and for us. Well, in one word again, propose a heartfelt or our gratitude, my gratitude on behalf of SRIBS, on behalf of our director, and to all the online participants, and also to Leda ma'am and Sir Son were here with us, or has been here with us all this time. So heartfelt thanks to you for coming over. And yeah, I'm coming to that. So we have our administrators, SO and AO with us, who are also taking pains to arrange this seminar. We are really thankful. So in one word, thanks to all. Thank you.
Thank you.